In this video, I will provide an overview of my course on the Go programming language. This is an animated visual online course for the complete novice. It is targeted at the beginner, but people with some level of programming knowledge should also be able to benefit from it. My name is Shahid Bukhari, and I am associated with the company AlgoPath. The full name of the course is Go Programming Animated, a Visual Introduction, and it is available at this URL, algopath.teachable.com. I will first describe the course in a few slides and then go on to show you excerpts from some of the many video simulations I have used in this course. The prerequisites for this course are very simple. You need a PC or laptop running Windows, Linux, or Mac OS. You need an internet connection. You need to have the ability to create a text file using a text editor of your choice. For example, Notepad, Vim, Emacs, etc. And you need to know how to open a terminal and run the command go run example.go. That's all you need to know, and I'm sure most people who have computers can do this or quickly figure out how to do this. What is the audience for this course? I have designed this course for 3 levels of participants. Students in school or college who plan to learn programming and wish to adopt a new and innovative language that is likely to be in great demand over the next decade. This is especially important in view of the current worldwide shutdown of educational institutions, which gives numerous young people the time to learn this language through the internet. Programmers with 1 or 2 years of experience who are proficient in 1 or 2 languages can use this course to become familiar with Go quickly and without much fuss. Professionals who are familiar with computer usage but have little or no programming experience and wish to learn one of the newest languages will also be interested in this course. The carefully crafted visual presentation and step-by-step narration of this course permits rapid absorption of the concepts of Go. The full course, available at this URL, is based on 3 modules with 10 lessons spread over 5 hours. There are 75 painstakingly developed program simulations made up of several thousand animation slides. All program sources are provided, and there is a number of interesting programming assignments suitable for self-study. I have nearly 40 years of teaching and research experience, and I am an enthusiastic developer of animated slides and presentations for my students. You can find my biography at this location. Now, for those who have some experience in programming, here are some things that may be of interest. Those who do not have any experience in programming in languages like C or C++ or Java can simply ignore this because I will not assume this knowledge in the course that follows. Go is been under development for 10 years. It is now in production use. It combines the brevity of C with the elegance of the Pascal family of languages. It eliminates many of the irritating features of C: break after each case, awkward declarations. Now functions can return in Go, they can return multiple values, which leads to great convenience. The for loop has been refined so that it has many capabilities, and while and do while loops are superfluous. Array bounds are always checked. Slices, which may be considered windows into arrays, uh, allow easy implementation of complex requirements. There is a runtime package which lets you probe memory allocation and garbage collection. And additional features, which are not in this course but may be included in future courses, include built-in support for parallelism, support for testing, and for web programming. Now, in this program, you will notice we have the usual first two lines, main and FMT, and the function main is the program or function that is executed first of all. And here we are. Once we come to this function, scope is open. This is the outer or main program scope. We can declare variables. Here we declare A, B, and C to be of type int. These are automatically set to 0 by the compiler. But we can, of course, change them. We change A to 2, B to 3, and C to 7. When we print out using println or printline A, B, and C, we get what we expect, 2, 3, and 7. Now we open an inner or nested scope. And in this scope, when we open it, we see a frame appears here. And two variables are declared, automatically set to 0. And these variables are A and C. These variables A and C shadow the outer scope's variables A and C. These are no longer visible. Now in this scope, only these two are visible. We set A to 5 and C to 9, and then print A, B, and C. We printed A, B, and C in the outer or main program scope. Now we are printing them out in the inner scope. And what happens here is that when we print them out, we see the values are 5, 3, and 9. 5, because the older A or the outer A is not visible. B, because the older B is visible, and C, because the older C is not visible. And so we have the inner A, the outer B, and the inner C here. It should be, yeah, inner C here. At this point, we can close the scope and everything in it disappears. And the shadowed variables pop back into life. And we can do a print line statement just as before. These will print out the outer A, outer B, and outer C, because that's all that's visible at this time. So here we go. 2, 3, and 7 are printed. 2, 3, and 7 are in memory. And the print line statement here corresponds to this line of output. The print line statement here corresponds to this line of output. With this out of the way, we close the scope, everything disappears, program is ended. Now here we have nested for loops. There is a for loop with a block or a scope extending from here to here, and this is executed 1 through 5 inclusive times. And this is a nested loop. The J loop, this is an I loop, this is a J loop. The counting variable for this outer loop is I. The counting variable for the inner loop is J. And we execute this for a variable number of times. We execute it for a value that is less than or equal to I. So what happens here? We execute for I is equal to 1, and then for J is equal to 1. And we print the star, and that's
it because we were only going to go up to the value of I. J was only going to go to the value of I. I can go back and show you. J was only going to go up to the value of I. When J becomes 2, we exit the loop and you print a new line and proceed with the next iteration of the outer loop. And that iteration has I is equal to 2, therefore we execute the inner loop for j is equal to 1 and j is equal to 2, which is I. So this is the first time, this is the second time, and for the third time the value of j becomes 3, so this for loop is terminated. We go to the next statement, which prints a new line, and we go back up to the outer for loop, the I loop. In this case, we have the value I equal to 3, so j will go from 1 to 3. Here we go. 1, 2, 3, and then j is 4 at this point, and so the for loop terminates. We go to the next statement, which is just going to print out a new line. We end the outer for loop and the block of the outer for loop and go back and execute it again, now for I is equal to 4. So you can imagine it's going to print out 4 stars and then exit the inner loop. The inner loop is going to print out 4 stars. 1, 2, 3, 4, and the next value of j would have been 5, which causes this for loop to be terminated. We go to the next line, which prints out a new line, and we go back to the end of the scope of the outer loop, and here we set I equal to 5. So the inner j loop is going to be executed from 1 through 5 times, and we'll watch that gently. 1, 2, 3, 4, 5, and at this point j is 6, which exceeds 5, this 5. Therefore this for loop terminates. We'll print a new line here and go to the bottom of the scope or block of the outer loop. At this point I becomes 6, so this for loop also terminates and we are ready to close the scope of the main program. We do that and the program ends. So now this pattern is a simple pattern, but you can write your own code to generate some patterns. I've given some exercises as well. The good or the interesting or useful part of these kinds of exercises is that it gives you a lot of experience in writing nested for loops, and you can check for yourself whether things are turning out the way the problem specifies, or they're generating a pattern in the way that you want it to be generated. We move on now to while loops. Well, there are no while loops in Go. In other languages such as C, while loops allow us to execute a block of code as long as a condition is true. C, being an elegant and minimalist language, that by which we mean it gets the most done with the least number of complications, uses a for loop in place of, or as a substitute for, the while loop. So this for loop will be executed as long as this condition is true. The for block is executed as long as x is less than or equal to 4. So let's march ahead. Now notice one thing. The variable we are testing for in the for loop must be declared here, okay? Because there's no way of running this form of loop without declaring the variable outside. So x is 1. For x is less than or equal to 4, we declare a variable s, print out its, or rather compute its square, and then print that out, the square of 1 being 1. It's hardly a surprise. We increment x at the end of the loop, go back, increment being done already here, the value of x is 2 at this point, and that is less than or equal to 4, so we proceed ahead. And at the end we increment x by 1, so that becomes 3. At this point x is still less than or equal to 4, so we can execute the loop body again, go back to the top, x is 4, 4 is still less than or equal to 4, we execute this again, and x is now set to 5 because of this increment. And when we go to the top, 5 is greater than 4, so we end this for, go on to the next statement, which is a closed scope, and at that end is this program. So we can see that we can execute a for loop in a form that becomes a while loop in other languages, and that was the intention in this program. Now this is a rather simple program which prints out squares and increments at the end. You could have a very complex block of code here where the x would be changed at various different levels, different parts of the block, and would cause whenever x was not satisfying this condition, you would exit this for. The next statement is, or the next animation is A and B are both 2. So if A is less than B, we check no, it's not less than B. So we go to the else part. We check, is A is equal to B? Yes, A is equal to B. So we print out A is equal to B, and this condition having been satisfied, the remainder of the else is not executed. However, we must close the scope of the else here, and having done that, we end the program. For that, we have the facility of the scanf function, and that facility is that this fmt.scanf function, in addition to reading the value into I here, it also returns two variables, n and err, which is the error. N is the number of values that were read when this statement was executed, and there is an error code err. We will not be concerned with the error code at the moment, and will use the underscore to signal that we don't care about it. So in this statement here, n comma underscore colon equals fmt scanf of and I. Okay, now scanf returns a value n if nothing is read. In other words, you've run out of numbers to read. It will return n is equal to 0. So that's valuable. We could have any number of values, and as long as something is being read, it will continue. If nothing was read, we know that the sequence of input variables has ended. So open the for scope. This is an infinite loop. There is no condition here. It's an infinite loop. It extends from here to here. And we start reading the values. First of all, we declare I to be of type int. We read in a value of I, happens to be 8. Is n equal to 0? Now, n is the number of variables that was read in that preceding scanf statement. And indeed, a value was read. Therefore, n is set equal to 1. It's not 0. So this if is not executed. We go on to the line after that if, after the scope of this if, and we print out 8 and its square, which is 64. At this point, we reach the end of the for scope, go back to the top, and start all over again. Int I is default 0. We read in a value from the input, and that happens to be -3. The number of values read is 1 during this scanf. So n is 1. N is, when we look at this statement, n is not equal to 0. So this if scope is not executed. We print out the value of I and its square, go back up to the top, and then repeat again. In this case, I is 11, and the value of 11 goes into this variable, but the number of variables read is 1. So this if is not executed. We print out 11, 121, end the for scope, go back to the top, again declare I to be 0 by default, and we try to read beyond this point, but there is no input value beyond this point. So I remains 0, which was the default value, but more important, n is now 0. In other words, the number of values read was 0. So we've come to the end of our list. So if n is 0, you break. Now you break out of the enclosing for loop. This is the enclosing for loop. You break out of it and go to the line after that. Okay. And that line is the last line of the program. We close the scope, end the program, and that's the end of this program. So this we can use the plus operator. Normally plus would be used in arithmetic. If A is 3 and B is 4, A plus B is the arithmetic addition. But this operator also applies to strings, and when it applies to strings, it represents the catenate operation, which means put one string after another. So that is the catenate operation. So let's start here. We allocate two strings, A and B. We input the first string, which is A, and we input the second string, which is B. First string A is fat and second string B is cat. So we now execute the catenate operation. B is equal to A plus B, which means that B is fat plus cat. So let's see. A remains unchanged at fat, but I've also printed out the length of A, which is 3. Now this is the interesting part. B, having been set to A plus B, is fat cat. Fat catenated with or combined with the variable A, so we get the variable fat cat, and the length of that string is 6. End the program. So what we've learned here is that plus can be used to combine or catenate, put one string after another string, and we also reinforced the notion of the length of a string, which can be obtained using the len function. First, look at this discussion. A dereference pointer can be used like an ordinary variable. So you can have something like star p is equal to star p star star q. So you are saying that the thing pointed to p is replaced by the thing pointed to p multiplied by, this is here star means multiplied by, the thing pointed to by q. So the symbol star can have different meanings depending upon how it's used. Int star p and star q in this statement, star signifies that p and q are pointers, and in this statement this stands for dereferencing, this stands for dereferencing, this stands for dereferencing, but this stands for multiplication, just like in ordinary arithmetic statements. So let's, with this in mind, let's move on to our program. X and y are declared to be 1 and 2. These are integers. P and Q are declared to be pointers to variables of type int. And since they've just been declared and not initialized, we have x and x in both of them, indicating that they're not initialized. When we say p equals and x, that means p is set to the address of x. P points to x. Remember, and x means the address of x. So let's execute this statement. P points to x. P is the pointer, x is the pointee, p points to x. P is set equal to the address of x. Q is set to the address of y. So Q points to y. This should be Q. Now we move on to the next statement where we print these values out to see what's going on. We print out star p and star q, the values pointed to by these pointers. So after dereferencing, we see that star p is 1 and star q is 2. Now we can change these variables. Star p is now equal to 3. The location pointed to by q is changed to 3. I'll go back. It was previously 1, but when we said star p is equal to 3, it meant go from p to its pointee and change that to 3. Similarly, q is pointing to a variable of type 2, of value 2, and when we say star q is 7, we get y changed to 7. Now we execute an arithmetic statement that involves pointer variables. Star p is set to star p multiplied by star q. This stands for multiplication, this star stands for multiplication, this star is stands for dereferencing, this stands for dereferencing, and this stands for dereferencing. So what happens? Well, star p, I'll go back. Star p is replaced by star p, which is 3, multiplied by star q, which is 7. So we get this. Star p is set to star p multiplied by star q. And we can print these out to check. P is 27, star p, sorry, is 27, and star q is 7. So this is an important aspect of the use of pointers, called dereferencing. Okay, now in this program we make a slice of type int with length 6. So here we are, length 6, and it's all pre-filled with zeros. When we print it out, when we print out the length of x, it's 6. When we print out the capacity of x, that is also 6. So what's the difference between these two? That will become evident later in the program. We can set specific indices of x to whatever we want. x3 is set to 27, x5 is set to 16, and we can now print out. What do we get? We get 0, 0, 0, and then 27 and 16 in the correct places that where we put them. We can now create a subslice which starts with index 2 and ends just before index 4. Starts in index 2, ends just before index 4. Print it out. Indeed, 0 and 27 is what we expect. What is the length? The length is 2 because this subslice has length 2. It contains 0 and 27. What is the capacity? Well, surprise, the capacity is 4. And this is an important concept. The capacity of this subslice is 4 because the parent slice x has more space after this index. So if we wanted to put more things in it using append, we could up to a maximum of 4. So this is our first brush with length and capacity, but we will see this in detail later on. So we have our functions. These are exactly the same functions we discussed in the earlier slide, the push function and the pop function. Let us go to the main program and let us create the stack, which is actually a slice, and declare an integer x. So the first thing we do is push onto s the number 3, and we then print what we can see. When we push onto s the number 3, well, it contains 3. When we push, next we push 7, what will the stack look like? Because it's being pushed from this direction, the stack will contain 3 and 7. Now we push -5. What will the stack look like? 3, 7 and -5. So things are being added from this end. Now we pop. Remember, last in, first out. So what was the last element? It was -5. When we pop s, we get -5 as the answer. The stack is now 7. When we pop x again, we get 3, and the element that we desire from the top of the stack is 7. And then we pop again, the element we get is 3, and the stack is empty. So this shows you that you can implement a stack very neatly using slice operations. And one will have need for this kind of operation in more complex programming later on in Go, as you program non-trivial programs with it. We declare two variables, x and y, to be int pointers, and the notation here is that an x indicates an unallocated pointer, a pointer which exists but doesn't point to anything. So if I now say new int, I create a variable of type int in dynamic memory and set its address to x. X is set to a memory address returned by new. So what happens? Okay, this is allocating memory sufficient for an int variable. X is the pointer, star x is the variable star x is the variable pointed to, sometimes called the pointee, and star x can be used like an ordinary int variable. So here is y. Both of these pointers x and y are allocated. They point to variables allocated in memory. We can now set star x to 3, which means that the location pointed to by x becomes 3. Similarly, we can set star y to 2, which means that the location pointed to by y becomes 2. So if I print star x and star y, I get 3 and 2, as you would expect. Now I can also do ordinary arithmetic on these variables star x and star y, and here notice that this star stands for ordinary multiplication, whereas the others are dereferencing operators. Now if I having executed this statement, y becomes 6, and if I print out x and y, I get 3 and 6. Okay. Now when the scope in which a dynamic variable was created is closed, the space is reclaimed by the garbage collector. Okay, a garbage collector is a program that runs periodically and finds all variables that are not pointed to and returns them to the pool of memory that is available for further allocation. In this regard, Go is like Java. It does not require malloc-free pairs as in C or new delete pairs as in C++. If you do not have any prior experience with these concepts, you don't have to worry, because Go has been designed to eliminate the complexity inherent in these concepts. However, we will in some of the later programs go into some details of what is going on inside the computer's memory, and so that by the end of this course you will have a fairly good understanding of how this garbage collection business works.